Hello and welcome, folks. We are back with day 2 of Advent of Code 2023. So straight away, I think it's safe to say that day 2 was a hell of a lot easier than day 1, at least the second part, that is, anyway. So as I was saying yesterday with the day 1s, and the first kind of week, we generally assumed that both parts, both 1 and 2, are going to be pretty easy, kind of thing you can knock out pretty quickly without too much of a challenge. They kind of threw a curveball at us yesterday with day 2's part 2 being quite complicated, or having a little bit of extra complexity we're not quite expecting yet, and also being just a little bit fiddly and having some quirks to it. This day 2, though, complete opposite. Pretty straightforward, no real tricks involved, just kind of got to do what it says, and the solution for it is pretty straightforward, really. You don't have to do any real mental gymnastics to figure it out, and again, there's no little trick or anything like that. So with that said, let's jump in. I think actually it's fair to say with this one, this is kind of an exercise in reading the problem and comprehending just what the problem is, because it's kind of wordy and it's not 100%, it's not super clear, I don't think, until you read the whole thing, exactly what it is, exactly what it's asking you to do. Now, I have to admit, I did this very early this morning because I had stuff to do. So I got up really early and I did it. And then I'm just now filming this video later in the afternoon. So with a second reading of this, maybe it will be apparent that it's actually quite clear. But anyway, let's jump in and let's talk about the problem. So, you remember from yesterday, we were in a trebuchet. We're going to be launched up into the sky. So we have been launched up into the sky. And now we have basically been launched to a floating sky island called Snow Island, which is where the snow comes from, it seems. You meet an elf, and he tells you that you have a little bit of a walk to get to where you need to look at for the snow or whatever. And in the meantime, he has a game he'd like to play as you're going. And so the game is what the puzzle, basically what we're trying to solve. So it's a little bit kind of convoluted, but basically he tells you that he has a bag, and in it, I'm going to call them marbles. They say in the solution cubes, but I don't know, I just kind of thought of them as being marbles in a bag. I don't know why, but marbles, cubes, whatever. He has these things in a bag, and they're different colors. So there's red ones, there's green ones, and there's blue ones. So what he does is he has his bag of marbles, he puts his hand in and takes out a random handful, and within that random handful there will be some amount of blue ones, some amount of red ones, and or some amount of green ones. So there can be any kind of combination, any number, any combination of subsets of those colors. So what he'll do is he'll put his hand in, he'll take them out, and then he'll put them back in, and then he'll put his hand in and take another set, and then put them back in and take another set, and so on and so forth. And the whole thing here is we don't know how many of each colored marble are in the bag to start with. So the first part of the challenge is he tells you, okay, imagine, for example, that there are 12 red ones, there's 13 green ones, and there's 14 blue ones. So what he is going to do is he's going to put his hand in, take them out, and show you the colors. And effectively what you have to do is you have to use your assumptive logic of there's 12, 13, and 14 to say whether that's true or false for the round of the game that you've played. So you see our input here is basically each game that we've played. And then in here, between each semicolon, is the handful that he's pulled out. And he'll do that multiple times in each game. So you have to say whether that's possible or impossible based on the assumption that there's 12 red, 13 green, and 14 blue. So as you go down to the list, it's not super clear at first, but you see down here, say with game 3, in this one, he pulls out a handful at one point that has 20 red cubes in it, or 20 red marbles in it. We've been told that, well, there's only 12 red in total, which means that this is like an impossible hand to have been dealt. Obviously, there's way more marbles in this bag than the assumption here. But what we're to do is we're to take that assumption, and then for each game that we have here, we're to say whether that's impossible or a possible outcome to have happened based on the assumption. So, think that's about it. So in this case, we have a few that are impossible. We've got this one, the 20 reds is impossible, and we've one down here that says 15 blues. Also impossible because there's not enough, and there's also one here then that says 14 reds, but we already saw 15 blues, so we know it's impossible, so we can kind of exit early there. So yeah, that's the logic. Now, the data doesn't have anything super complicated in it. Basically, all we need to do is loop through each line, each game, and we need to loop through each subset, so each handful of marbles that the guys pulled out, and check the values. And we can sort of exit early if we find that there's a number that goes over our limit, and that would be an impossible one then. Or if we don't go over any limits, then that's a possible solution, and we would take that as being one of our true cases. So at the end of it then, all it wants you to do is, it wants you to sum together the game IDs of all of the possible cases. So in this case, that would be, where is this? So the possible cases here are 1, 2, and 5. So the sum of those is 8, which is the answer to this one. So let's have a look at the code. Again, this isn't wildly complicated code, but it's a little bit involved. It's just kind of a lot of nested loops and a lot of parsing of the data. Again, the data is not complicated. There's nothing wild in it. It's just sort of the way it's done out in a string. You just have to parse it and break it up. So we start up here. I created this little hash up here, which has our limits in it. So we've got our blues, our reds, and our greens with the number of each that is the max you can have. I'm making an array, 2 empty arrays, one for all the possible game IDs to go into and one for all the impossible game IDs to go into. Don't have to do that. Just wanted to keep track of them for debugging if anything went wrong. So first thing I do, big loop that goes through every single line. And here we're just basically splitting up this segment again. So there's a lot of this split function is being used quite a bit in this to break out all of our data. So from this, we'll get the list of all the subsets, and we'll also get the game ID. And I set a variable up here at the top, which is possible. So I assume that's true. And effectively what we will do is then we'll iterate through each of those red, blue, green values that's in the list. And if we hit one that overflows the limit, we'll turn that variable to be impossible. And then later on, we use that to decide which array we stick the game's ID into. And yeah, that's it. So if we go through all these nested loops and we don't find an impossible outcome, then it's possible is true, and then we can put it into the possible list. So yeah, then again down here, we'll do a split operation on a semicolon to get us a handful basically, and then we'll do a split operation on a comma so that we see all the colors that are there. And yeah, then we just go down here, we check, basically we have this conditional that just checks the number that we got against the color. We look it up in this map to find the max, and if that overflows it, then we set possible to false, and we go on, move to the next iteration. I also have 2 break conditions here, so if at any point possible gets flipped to be impossible, we'll just exit out and we'll just basically just skip through all that without doing any processing. Just a little shortcut. Doesn't really make much of a difference here, but in a bigger type of application, this shortcutting would, or a bigger problem with more computational intensity, this would get you out of there faster. So yeah, that's it. We go through this loop, figured out whether that game is possible or impossible. We've added it to one of these lists. And then at the very end, we take the list of all the possible game IDs and you sum them together. And that's it. Simple as. So we can run that, 2, 1, and the sample. And there we go. We get 8, which is the answer. And if I run it on my input, I get same answer. It's not terribly fast because there's quite a lot of looping in this, so it's probably a smarter way you could do it, but it's pretty quick. It gets through it, does the job. Okay, cool. So let's have a look then at our part 2. So for part 2, the game is basically the same, except, excuse me, in this case, instead of trying to determine whether each game is possible or impossible based on some arbitrary conditions, instead what we want to do is we want to try and figure out for every game what would be the minimum set that would be in the bag for it to be a possible game. So for our first example here, we've got 3 blues, 4 red, 2 green, 6 blue, and 2 green. So for this to be an actual game, or for this to be possible, we must have at least 4 reds in the bag. We also must have at least 6 blues in the bag, and we also must have at least 2 greens in the bag. If you don't have enough of any of those, this would be an impossible game. So with that in mind, we can think about what the general thing we're trying to do here is. And basically all we're trying to do is find the largest blue value, the largest red value, and the largest green value in this entire loop, in this entire set of draws of goes of the game. So if we find the highest value of each of those for each game, that tells us what the limit is, basically. And that's what we have to get for each game. So then the answer is you take each of those values, you multiply them all together, and then you sum them together for all of the games, and that gives you the answer for the puzzle. So, excuse me, let's have a look at the code for that. And the code for this part, it's actually shorter, simpler, I think, because there's just less checking stuff involved. So we have the same basic structure. I pull out the game ID, and I do this splitting logic to have these two lists. Excuse me, sorry. That's better. So the difference in this case, though, is that I don't have 2 arrays trying to maintain the impossible and the possible games. Instead, all I'm trying to do is I'm just trying to determine the max values of each of the colors for each game. So as I do this nested loop, I basically set up this hash up here with the values. So this hash will effectively be the same structure as this. The key is the color, and then the value in this case will be the max value, or it'll be the first value that's seen. So if the first value is the only value, then it will be the max. Otherwise, it will give you the otherwise we need to replace the value. So that's all we do down here. So we get the value, and so we get the color and we get its value, and then we look at the this values hash here. We check the color, check if it exists, and if the new value that we've just gotten is greater than the existing value, and if so, we set that value, and that's it. And yeah, literally that's it. That's the entire thing. So once we've gone through all of the colors, we now have a hash that has the 3 values in it, and then all we have to do is do this little line here, which this just is all this does is it just multiplies together the 3 numbers. In this case, it's confusing of values. Values is a hash. Values is a property of a hash, which just returns an array of all of the values of a hash. And then the inject function will just basically multiply them all together if you pass in the multiplication operator, as simple. And then at the very end, I could just sum all those together. That's it. Done. So yeah, it's pretty simple. It's actually more straightforward than the first part, I think. It's a little less. I think it's a little less convoluted. I think once you get that splitting logic, it's quite simple. And it's less arbitrary as well. The first one's quite arbitrary. It's like, well, here's some numbers, just check them off. Now, I'm not sure if they sort of intended that you would leverage that in some way, the first part, to solve this part. Like literally the only part that I've reused is the way of parsing the data, but my actual solutions for both are kind of different. So it's not a case of where you do the first part and that exactly you use that then exactly to do the second part, which is very often the case with these problems. Like, now that can come down sometimes to your understanding of it. Sometimes you will get the exact understanding for the first part that then it works perfectly for the second part. Can be a bit of coincidence. But there is kind of, I found there is sort of a way of thinking that they want you to have with these puzzles. So practice kind of lends it to that. But in this case, I found they seem to be quite different, except for I was able to exactly reuse the parsing logic of each one. So not a terribly complicated day, but still kind of, a good puzzle. It gives you kind of satisfying to get it out. I haven't ran it, which I always feel like I must do to prove that I actually do these and that they work. That is the answer from the sample. And for my input, there we go. And it's funny, like I said, it's the second part's less complicated and it actually runs faster. So I guess it's slightly less computationally intensive as well. So yeah, that's it for day 2. I hope you guys enjoyed it. And yeah, we're going to come back tomorrow for day 3. So I hope you guys are all having fun. Hope you're having as much fun as I am anyway. And yeah, I will see you guys tomorrow.